Welcome to the second half of our discussion of general relativity. In the first half, we basically identified gravity and acceleration. Gravity is as gravity does, and what gravity does is accelerate stuff. But as we saw with special relativity in this week's other topic, motion alters space and time. So, since gravity is essentially equivalent to acceleration, gravity will alter space and time. The more common term here is warp space and time. We talked about that somewhat in the special relativity case, but we're going to need to go into a little more detail to understand the interactions between mass and space-time. So let's take a case that's kind of in between a special relativity case and a general relativity case, and we'll build out from there. So we're going to imagine really fast circular motion. So circular motion at an approximation of the speed of light. Excuse me. So with circular motion, it's not constant velocity because the direction is constantly changing, but the speed isn't. So we need to figure out how motion is going to alter space in these circumstances. Here is Brian Greene, the same physicist from whom I stole the light clock example. Here's his way of understanding this case. So a ruler measuring the circumference will have shrunk when judged from the center. The center is not moving. The circumference is moving at a significant fraction of the speed of light with respect to the center. Lengths shrink in the direction of motion. So if you're measuring the circumference as judged from the center, you'll be doing so with a meter stick that will have shrunk. But a ruler measuring the radius of the circle won't have shrunk because that's perpendicular to the direction of motion, right? So in a special relativity case, you get, as it were, less wide but not less tall if you're moving just on the x-axis with respect to me. Same principle is at work here. The circumference of the ruler, the circumference of the circle will be measured with a ruler that has shrunk, but the circumference of the radius will not. What does that do? That means the geometry of this bit of physical space is no longer Euclidean. You're not going to be able to identify the circumference with pi times the radius times 2. So I'm not holding you responsible for remembering your geometry from high school, but that's how you figure out the circumference, right? Pi times the diameter or pi times twice the radius. So take my word for it if you don't remember that. But the punchline here is physical space isn't Euclidean under these conditions. That's what we mean when we say motion and acceleration and hence gravity warp space-time. So as you try to understand the physical properties of that space, you have to use different geometries. The space will, in Euclidean terms, deviate from the space a circle, scare quotes here, ought to have. So let's try to unpack this in terms of the Leibniz-Newton debate with which we are semi-familiar. Newton was wrong in thinking that space is a neutral arena in which objects happen to be located. Space interacts with mass. It responds to the presence of objects in it. Imagine a sheet that's been stretched out and you place a bowling ball in it. That changes the space occupied by the sheet. So Newton was wrong about space being a neutral arena. Leibniz was wrong about space being nothing but the set of all possible distance relations. Space, causally and physically, interacts with objects, and so it's thingier than Leibniz thought, but it's not the neutral propertyless thing that Newton thought it was. Now let's connect this to Galileo's famous thought experiment about the ball on a frictionless plane. So if you place a marble on a flat sheet or on a frictionless plane, give it an initial velocity, it will move in a straight line forever. Now place a bowling ball on that sheet and the marble will move in a curve. If it weren't for friction, the marble would go around the ball indefinitely with a certain range of starting velocities. That's how motion works. Basically, the way to think of it is everything is moving in a straight line, but in the presence of massive objects, straight lines in that kind of space are a curve. So, what we call gravity is not the mysterious action at a distance, immediately effective across vast swaths of space pulling force. It's not a pulling force at all, really. It is the curving of space by mass. And that curving of space by mass affects motion because of this curvature. So, the curvature of space increases with mass and decreases with distance in just the way that Newton describes. And so Newton gets the math essentially right, except he doesn't have an element, a time element for the dispersal of this force. But he thought of it as an invisible, mysterious rope kind of thing, and that's not what it is. What it is mass and space interacting with each other, and objects moving in straight lines in spaces that are, from Euclidean standards, funny. In a certain sense, this is Leibniz's revenge, too, because we've got a least action principle going on here, which Leibniz had said amounts to final causation, not mechanism, right? Objects are taking the shortest possible path as if it's Aristotelian teleological causation, and they're lazy. How mechanical, how much we have fulfilled Kepler's clockwork model is a super interesting question. Einstein has come closer than Newton did because Newton had no idea how gravity works. With Einstein, we do have a mechanism. It's the curving of space-time, but Leibniz would come back and say, you still have a least action principle. You're still minimizing or maximizing certain values, and to Leibniz anyway, that looks like teleological, not mechanical causation. Okay, a few more details just to not mislead you too much. That bowling ball on a sheet analogy is the classic analogy. And it's not wrong, it's just dangerous if you don't read it carefully. So in that analogy here on Earth, right, it's gravity pulling the bowling ball down. But gravity isn't the pulling down, because we don't want gravity doing double duty here. Gravity is the warping of the sheet, the changing of the shape of space-time. And it happens in all directions, not just down. So that is a simplifying analogy that uses gravity here on Earth to try to explain what gravity would look like in space. So the way in which we get the bowling ball to deform the sheet is by using gravity. But we don't want to double count gravity. So in space, you just picture the sun deforming the space around it without there being anything, as it were, pulling it down. And then the analogy does its work. So, despite what you probably thought before this class and what you were probably taught in high school, there is no mysterious action at a distance pulley force. It's not pulling. Space is kind of stuff-like, and we are feeling space when we feel gravity or acceleration. The physicist John Wheeler puts it by saying mass grips space by telling it how to curve, space grips mass by telling it how to move. So, we are falling through space. This is not as weird as it sounds. Newton figured out how to launch a satellite in the 1600s, which is an amazing achievement. And the only technology he had access to was basically a cannon. And so if you launched something from a cannon at the right angle so that it was falling more slowly than the Earth was curving away from it, you've just launched a satellite. You did it by launching something in a straight line from Earth. It ends up going in a curve around Earth forever because that straight line goes into a curved space. If you ever fly internationally, it sort of looks like a curve as it's projected onto the Earth, but the pilot is going to experience herself as flying in a straight line. It's just that space curves away from her. So, the planets are moving around the sun in a straight line in a curved space. It's called a null geodesic if you're keeping score at home. So, we focused on space here, but gravity warps space-time, not just space. The warping of time, or the time part or aspect of space-time, is surprisingly small. If you could move a clock a few miles from the surface of the sun, it would be very difficult to detect the extent to which it slows down. But super strong gravitational fields, like just outside the event horizon of a black hole, can really slow time. You couldn't hover just above the event horizon, but if you somehow could, and you stayed there for what you regarded as a year, when you returned to Earth, about 10,000 years would have passed. But that kind of gravitational field involves squeezing the sun down to a 2-mile radius. And so a teaspoonful of that compressed sun would weigh, see, I need to edit my writing too sometimes, weigh about as much as Mount Everest. So Newton fainted at instrumentalism about gravity and fainted at realism about gravity. It's not clear exactly what he thought gravity was. It's not entirely clear what he thought space and time were. Were they things or aspects of God? In a 100 level class, we're not going to go into those details. But once we've got general relativity, realism about Newtonian gravity is not an option. There is no mysterious action at a distance pulley force. There is the warping of space-time by the presence of mass, and then objects moving in straight lines through in a certain sense altered, bits of space-time. So that's how motion works. The warping of space-time is transmitted at the speed of light, and so now we've reconciled special relativity and Newtonian gravity by providing a new mechanism. So to sum up, Einstein sees that gravity can be understood through the lens of acceleration. Acceleration is a kind of motion, and so is going to have the same kinds of effects on space and time that constant velocity motion does. They'll be changing, but same kinds of effects. Gravity is understood as an accelerator, and so gravity alters space-time. Chew on this for a little bit. Think about questions to throw at me. Thanks, as always, for your time and attention.